Okay, so we're going to look at this problem. Dentists use x-rays to image their patient's teeth and bone. The x-ray tubes that generate x-rays contain an electron source separated by about 10 centimeters from metallic targets. The electrons are accelerated from the source to a target by a uniform electric field with a magnitude of 100 kilonewtons per coulomb, as drawn in the figure. When the electrons hit the target, x-rays are produced. What is the potential difference between the electron source and the metallic target? So we have two numbers here, 10 centimeters and 100 kilonewtons per coulomb. I'm going to redraw my picture so it just shows two parallel plates because that's what we're used to. And that's the only situation the uniform electric field where our equation works.
Mm-hmm.
And our equation says that if this is delta V and this is E and the physical separation is D, then we have a relationship between the voltage, the electric field, and the separation that says voltage difference is equal to ED.
Okay. Wait, is it? Well, okay.
Yes, that one. So we just need to plug in our numbers. 100 kilonewtons per coulomb. That's a volt instead of coulomb. Kilonewton per coulomb times, and it says 10 centimeters, but what am I going to use?
Meters.
Yes, 10 meters. And so that's equal to 10 kilo. What's a newton times a meter?
Newton times a joule.
Yes, so that's 10 kilojoules
right.
per coulomb. But a joule per coulomb is a volt, so that's equal to 10 kilovolts.
Okay.
So now we have the voltage difference, and then we have part B. In part B, I'm just going to rely on U. It says, what is the kinetic energy of electrons when they reach the target, assuming they start from rest?
Okay.
So how can we find the kinetic energy?
Kinetic energy. Well, kinetic energy is equal to the negative potential energy.
Okay, changes for both.
Oh,
yes.
change. Yeah, the change in.
So we started with the work-energy relation. Work non-conservative is equal to change in kinetic energy plus change in potential energy. But this is only a conservative force. The only force acting on it, we're ignoring gravity because we say that's really small compared to the electric force. So the only force acting on it is the electric force, which is conservative. So 0 is equal to change in kinetic energy plus change in potential energy.
Mm-hmm.
Therefore, the change in kinetic energy is equal to minus the change in potential energy. So what's the change in potential energy?
Change in potential energy is 1/2 m.
Well, that's the kinetic energy is 1/2 m
Sorry.
squared. Change in potential energy. The definition of voltage.
Q, like the charge times volts.
Right. We define the voltage difference is the change in potential energy over the charge. So the change in potential energy has to be the charge multiplied by the change in voltage.
I didn't even look at that one.
And so that's going to be minus 1.602 times 10 to the minus 19 coulombs, because that's the charge of an electron.
Mm-hmm.
And then our voltage difference of 10 kilovolts, I'll go ahead and put 10 times 10 to the third, which of course is 10 to the fourth volts. That's our change in kinetic energy. And if it started from rest, kinetic energy final minus 0 is equal to that. So our final kinetic energy is just, that's 10 to the fourth, 1.6. Oh, we don't need to have a calculator. Minus 19 plus 4 is minus 15.
15, yeah. That wasn't bad.
No, it turns out that was easy. It's kind of scary. You wonder if you did it right when it's so easy.
Yeah.
I will come here. Yeah, that one was so quick.
Okay.
So we had delta V was 10 kilovolts and 1.6 minus 15 joules. Look at that. Rock star.
Nice. Does this one?
Okay, what do we need to put across for the multimeter? How many is it volts, right?
I'm not sure what your question is. What do we need to put across for the multimeter?
Sorry, for the measuring the low resistors with the multimeter. What? How many or what? What are we on the dial?
Okay, on the dial.
There we go.
Okay, so the dial. Okay, so first of all, when you're measuring the resistance, you have it. One is in the common and one is to the one on the right that has everything that's not current for the two plugs that go into the multimeter.
Okay.
And then you take the dial around.
You said on the very right, correct?
Hmm?
The far right?
Yes, the far right.
Okay, those are
And then
plug into.
you bring the dial around and just start at the lowest one, which is up to 200 ohms. Now, I know your resistance is bigger than 200 ohms, and so it's just going to show one on the left column and then blank.
Okay.
And that means too low, go higher. You go to the next one, which goes up to 2,000 ohms. Depending on your resistor, you might read a number there.
Okay.
If it's on that one, because it says 2,000 ohms, it says that it's going to read in units of ohms with a maximum of 2,000.
Okay.
If it still shows the one, then you go to the next one, which says 20 kilo ohms.
Okay.
In that case, it's reading units of kilo ohms with a maximum of 20.
Okay, cool.
Yes, that's going to be on the recording. Close. Okay. Will the electric field strength between two parallel conducting plates exceed the breakdown strength for air, which is 3,000 or 3,000? It's 3 million volts per meter. It's 3,000 per millimeter. If the plates are separated by 2 millimeters, then the potential difference is 5 times 10 to the third. So tell me, how do I approach this? What's the first thing I should do?
Draw a diagram?
Yeah. So here's my capacitor plates. I have a separation of 2.00 millimeters. And I have a voltage difference of 5,000 volts. How do I find the electric field?
Electric field is volts over distance. Not sure if that's it.
No, that's exactly it. And so that's going to be 5,000 volts over 2.00 millimeters. Now, since that's millimeters, it means we're going to have a 10 to the third. So that's 5 divided by 2 is 2.
How did you know that was a 10 to the? Okay. Oh, like for the. Gotcha, sorry. For the denominator.
Yeah. Here. There.
Makes sense.
Or I could have done it this way. 5.00 to 5. I got sloppy. Times 10 to the third volts. I assume 3 significant digits over 2.00 times 10 to the minus third meters. So 5 over 2 is 2.5. 3 minus a negative 3 is 6. This is the easiest way to do your math, right?
Okay, cool.
So there's our electric field. Now we go back to the question. Will the electric field exceed the breakdown in air?
No.
Nope. Close, but we're safe. And with that, we need to call it there.
Okay. It's still helpful. Thank you.
Yeah.